Section 4.1, Linear Functions. Representing linear functions. The function describing the train's motion is a linear function, which is defined as a function with a constant rate of change, that is, a polynomial of degree 1. There are several ways to represent a linear function, including word form, function notation, tabular form, and graphical form. We will describe the train's motion as a function using each method. Now, representing a linear function in word form. Let's begin by describing the linear function in words. For the train problem we just considered, the following word sentence may be used to describe the function relationship. The train's distance from the station is a function of the time during which the train moves at a constant speed plus its original distance from the station when it began moving at constant speed. Now, the speed is the rate of change. Recall that a rate of change is a measure of how quickly the dependent variable changes with respect to the independent variable. The rate of change for this example is constant, which means that it is the same for each input value. As the time input increases by 1 second, the corresponding distance, the output, increases by 83 meters. The train began moving at this constant speed at a distance of 250 meters from the station. Now, representing a linear function in function notation. Now, another approach to representing linear functions is by using function notation. One example of function notation is an equation written in slope-intercept form of a line, where x is the input value, m is the rate of change, and b is the initial value of the dependent variable. Now, in equation form, we have y, which is equal to mx plus b. In function notation, we write f of x, which is equal to mx plus b, where y and f of x mean the same thing. Now, in the example of the train, we might use the notation d of t, in which the total distance, capital D, is a function of the time t. The rate m is 83 meters per second. The initial value of the dependent variable b is the original distance from the station, 250 meters. And we can write a generalized equation to represent the motion of the train. So d of t is equal to 83t plus 250. Now we can also represent a linear function in tabular form. A third method of representing a linear function is through the use of a table. The relationship between the distance from the station and the time is represented in Figure 2. From the table, we can see that the distance changes by 83 meters for every 1 second increase in time. So for t, at 0 seconds, you add another second to get 1, add another second to get 2, add another second to get 3. And then the distance goes from 250 meters at 0 seconds, and then adding 83 at 1 second to give us 333. Adding another 83 meters with another second gives us 416, and then adding another 83 meters gives us 499. Now, Q&A. Can the input in the previous example be any real number? The question is no. The input represents time. So while non-negative, rational, and irrational numbers are possible, negative real numbers are not possible for this example. The input consists of non-negative real numbers. Now, representing a linear function in graphical form. Now, another way to represent linear functions is visually, using a graph. We can use the function relationship from above, d of t, which is equal to 83t plus 250. And we want to draw the graph, represented you can see in Figure 3. Notice the graph is a line, and when we plot a linear function, the graph is always a line. Let's take a look at this function. So we have d of t, which is equal to 83t plus 250. Okay, so we know that the slope is 83 over 1, and the y-intercept is 0 to 50. So I want you to look at the graph here. The graph goes all the way up to 0 to 50, and then it uses the slope to go up 83 units and then to the right one, up 83 units to the right one to form that line. Now, the rate of change, which is constant, determines the slant or the slope of the line. The slope tells us whether it's going positive or negative. Now, the point at which the input value is 0 is the vertical intercept or the y-intercept of the line, which is what we have here. We can see from the graph that the y-intercept in the train example we just saw is 0 to 50, and it represents the distance of the train from the station when it began moving at a constant speed. Now, notice that the graph of the train example is restricted, but this is not always the case. Consider the graph of the line f of x, which is equal to 2x plus 1. Ask yourself, what numbers can be input to the function? In other words, what is the domain of the function? Well, the domain is comprised of all real numbers because any number can be doubled, meaning multiplied by 2, and then adding 1 to it.